In this lecture series, I intend to prepare some lectures on topics that I feel are extremely necessary to learn or know and are of introductory nature. Anyone wishing to learn about this subject called physics can go through these lectures. We are intelligent beings, and our intelligence has given us the power and ability to describe things around us. We describe ourselves, we describe the region we are in, we describe our neighborhood. Coming back from college, we describe the events that happened there. We look at the moon, the stars, and want to express our feelings. And to do this, we need a language. How good, how bad, how beautiful, how ugly, how much soothing, how much disturbing, and these are the aspects we describe. But we have to keep in mind that these expressions of our feelings of being good, bad, loved, hated, feeling of relief, feeling of anxiety, etc. In physics, we are not concerned with these things called feelings in general. We are interested with the physical aspect in general. For instance, how far is your college from your house? How can I go to your friend's house? Give me the address or location. How many stars did you see in the sky last evening? In short, in physics, we are more interested with location of objects, extension of objects or size of objects, formation of objects, to understand the nature, why is it the way we find it. In this lecture, we are interested to describe location of things around us in an unambiguous manner, meaning that there should not be any ambiguity, should not be any misleading description. The description should be to the point and precise. In short, it should be a scientific description. In physics, we use certain terms to do this, and the terms are up or down, left or right, north, south, east, west, left-handed, right-handed, clockwise, anti-clockwise. These are the terms needed to describe a location of an object in an unambiguous, systematic, understandable and precise manner. Now let me come to what I mean by description of location of objects. Consider the case of a spider resting on the ceiling and a child looking at it lying on the floor. The child would describe the situation by stating that the spider is 3 meters up on the ceiling, which essentially means that the child is down below and the spider is up above, because measurement is made from the child. An alternate statement from the viewpoint of the spider might be that the child is 3 meters up on the floor, which means that in this description the spider is below and the child is up, because measurement is made from the spider. Clearly, here we have two observers, and the description of the two observers do not match, they are different. And this is not a bothersome situation, it is perfectly okay. What is important in the two descriptions of the same thing is that there are two observers separated by a distance of 3 meters. Which is up or which is down is not a matter of concern. Ceiling may be called up or down, and the floor may be called down or up. We can cite another example. Consider a king and his queen seated side by side. and A, B, C and D are looking at the couple, what would be their descriptions? So A will say that the king is sitting to the left and queen is to the right. But B will conclude just the opposite. To B, queen is to the left and king is to the right. While C will conclude that king is nearer and D will say that the queen is closer. But all agrees that king and queen are sitting side by side. Let us take another example. This is east, west, this is north and this is south. And B, C and D are friends who wish to go to their common friend A's house. And they would have to go in different directions to do that. For instance, B has to move towards south and then towards west to reach A. C has to move towards north and then towards west to reach A, while D has to move entirely along west to reach A. We'll come to another interesting example now. Take the case of a circle where a particle or a bead is moving and it moves from X to Y. So this is the circle, this is the bead, and these are two positions, and the bead or the particle moves from X to Y along this circular track. Now consider two observers, one is A and the other one is B, and they are observing the movement of the particle or bead from position X to position Y. First come to A's description. To A, the movement is not how a clock's hand moves. A clock's hand moves in this direction, but here the particle moves in this direction, which is against the movement of the clock's hand. So it is anti-clockwise movement. Let me try to re-describe it using my palm. Now take the right hand, place the palm across the circular track and follow movement of the particle from X to Y. So here it is. So it is right-handed. So A's conclusion is that the motion is right-handed and anti-clockwise. Now let us come to the conclusion made by B. Now to B, the movement of the particle or bead from X to Y is similar to the movement of the hand of a clock. So the motion is clockwise. Let me try to re-describe it using my palm. So now I have to put my left hand across the circular track and follow the movement of the particle from X to Y. And here it is, so the movement is left-handed. So B will conclude that the motion is left-handed and clockwise. Obviously, the description of A and B are not identical because their relative positions with respect to the circular track are different. However, they both conclude that the angular separation of the two positions X and Y is 90 degrees. Similar conclusions we can end up with if the movement of the particle is viewed from up or from down. Let us view the movement of the particle from X to Y from above. If this was a clock and this was the hand of a clock, it would move along this direction. So the movement is clockwise. Now if I put my left palm across the circular track and curl my fingers, then this would indicate the motion of the particle from X to Y. So this is left-handed motion. Now if we view the motion from below, then it is clear that a clock's hand does not move in this sense, but it will move in this way. So it is anti-clockwise movement, and let me re-describe it with my right hand. So if I place my right hand across the circular track and if I curl my fingers, then it would indicate the movement of the particle from X to Y. So it is a right-handed movement. Now be it clockwise or anti-clockwise, left-handed or right-handed, whatever, all observers will conclude that the angular separation between the positions x and y is 90 degrees. We come to conclusion of our discussion till now. The same thing when described by different persons appear to be different, but some quantity are invariant. As for example, distance of separation. For instance, the 10-meter separation between the spider and the child in the first example, or the 90-degree angular separation between positions x and y in the previous example. This means that the descriptions are equivalent. The apparent difference in description is because our relative locations are different. Let us now address how we can describe things. The systematic description of objects is done by building a coordinate system, or by erecting or placing a reference system or axis, that is, by using an unbiased observer. We study now how to build a coordinate system. In the next lecture, IN1b, we will take up various coordinate systems that are used in physics. And in this lecture, we will elaborate on how to build the coordinate systems. First, the region we find ourselves and we are eager to describe, that is the expanse, the stretch around us, is called space. And we are about to describe space using certain terms that were used in 300 BC. BC means before Christ. The terms which are the basic elements or building blocks of any meaningful discussions are point, distance, angle. And with these terms we will build the coordinate system. These are the concepts we are extremely familiar with and are essential components of what we call Euclidean geometry. Euclid, an ancient Greek mathematician, wrote a book entitled The Elements, which consists of all the rules of geometry. He is called the father of geometry. In physics, we will be using these terms umpteen times, that is, we will be using them over and over again: point, distance and angle. We will come to these soon. Now, space studied by Euclid with his geometry, called Euclidean geometry, is denoted by R1, which is 1D, R2, which is 2D, and R3, which is 3D. And we can simply extend to higher dimensions, and the technique will be obvious at the end of this lecture. Though going to higher dimension is an abstraction which involves nurturing some ideas that cannot be put to direct test, and the need for this abstraction or going to higher dimension is not what we will discuss in this lecture and might be dealt with in a separate session. Let us mention the essential or inherent concepts regarding description of space by Euclid, by Euclidean geometry. Space is the region around us, and this stretch is essentially continuous. We cannot think of this space to be discontinuous or fractured, broken or split apart in any way. We move in space. Earth, moon, stars all move in space, and description of all movements is done by thinking of points moving in space. Now, to describe movement of points in space meaningfully, we attach 2 points or objects whose motion we are interested to study with a set of finite ordered numbers which are called coordinates. In 1D, we require one coordinate, while in 2D, two coordinates will serve our purpose. In 3D, we need three coordinates to describe motion of points. Now, it is clear that we have to handle coordinates as they will change with the movement of object. So, we have to use real numbers as coordinates, which represent a continuous quantity or variable with which we can represent distance in a direction along which a particle or object moves. What is the significance of such choice of coordinates? The significance is that if we use coordinates, then the problem of geometry involving motion of object in space will translate to problem involving numbers, which we can handle, that we can analyze and solve using ordinary algebraic rules. And here are the rules, where x and y are variables, a and b are constants. For instance, we can add the numbers 5 and 7 without thinking of the order. We can multiply 5 and 7 without thinking about which one to be placed first, and so on and so forth. We next define the essential elements, namely point, angle, distance, and you will come across certain things like symbols and techniques that are used widely in physics. Let us define point. A point is something, an object or a position that has no extension, no breadth, no depth. That is, we cannot attach a size to it. Next comes the angle, and you already know the terms: right angle, acute angle, obtuse angle, reflex angle, etc. An angle between two curves is the same as the angle between their tangents. Now let us come to distance. Any 2 points can be joined by a straight line. Say P is a point described by coordinates x and y, while Q is another point described by coordinates x plus dx, y plus dy with respect to origin 0, 0 here. And suppose they are very close points, and this is indicated by the separation dx and dy, dx along the x axis and dy along the y axis. So this is x and this is x plus dx, while this is y and this is y plus dy. Now our primary aim is to describe distance, and so we should clearly specify the technique to measure distance between 2 points. For that, we use techniques of Euclidean geometry. The distance we are interested with, that is PQ, is connected with distances PR, which is dx, and QR, which is dy, through Pythagoras theorem. And so we have PQ square equal to PR square plus QR square, that is ds2 is dx square plus dy square. Here ds2 represents square of the distance PQ. Pythagoras was an ancient Greek philosopher who was on earth between 570 to 495 BC and is famous for Pythagoras theorem. Now again back to the rule which the space manifests because of our use of Euclidean geometry. The rule is that the distance between 2 points can be expressed as under root the sum of squares. And very importantly, the space is such that in the expression of distance there will be no cross term. like dx dy, dy dx, and so on. This is an extremely important rule or characteristic of the space we are describing using Euclidean geometry. The nature was observed by many great people, great thinkers called physicists, and they gave laws to describe nature, and we study these laws. And to make the laws evident, we write the laws using mathematical expressions. Mathematics, when used to write down a law, reveals the law of physics, that is, reveals the law of nature in its full glory. Mathematics exposes or uncovers the statement of the law. This is to be understood properly. The power of mathematics, when used by physicists, unfurls and exposes nature. A teacher compared this beautifully as follows. A physical law is like a hot kettle. You use it, you see it, you touch it, you understand a bit of it. Now lift the lid of the hot kettle. The steam that gushes out makes you wonder about the power of the substance compressed in the bottle. Now that lifting of lid is like applying mathematics to physics. If you do it, you get the beauty out, which now you can touch and taste, feel and applaud. In this lecture also, we will see how mathematics is used and what its power is. Another thing is that just as we can have two or more names, say a real name given by your parents, a nickname by which your friends might call you, or a disguised name may be used to conceal identity. Similarly, we can have various notations and we will use them to make things simple. Notations are extremely important, as proper choice of notations makes laws look simple, bring elegance, simplicity and compactness to a theory. It is a good practice to change notation when needed and not to stick to only a single notation. Let us represent x by x1, y by x2, and so xy is x1, x2. Now what is the advantage of such notation? Replacing xy by x1, x2? The advantage is clear at once. Suppose we wish to extend dimension. Such an extension is obvious in x1, x2 system because the third dimension will be x3 and the fourth one, if we add, will be x4 and so on. In case of xy, the third dimension would obviously be z, but fourth one, if we add, will be anybody's guess because the rhythm ends with z and we have to make choices like P or U, etc. In a nutshell, choosing x1, x2 sets the rhythm and we automatically sail into higher dimension. At least there is a theoretical advantage and simplicity in handling the coordinates. So this is a smart and elegant choice. Now, be that as it may, let us move on with this choice. What we get here is ds2 is equal to dx1 square plus dx2 square, and we can write it as follows. This is the square term and this one is the second square term, and here we find no cross terms, so if we write dx1 dx2 we have to attach a 0 here. If we write dx2 dx1 we have to attach another 0 here. Now there are certain mathematical symbols that make life of physicists very simple and keep them free of anxiety, and one such symbol is the Kronecker Delta symbol. It makes the language of physics brief and compact, and of course elegant and stylish. The Kronecker Delta symbol was introduced by a German mathematician, Leopold Kronecker. And what does it represent? Consider two variables, one is alpha, one is beta, and suppose they assume discrete or discontinuous values, say integral values, negative, 0, positive. Then if two variables do not match, then the value of the symbol delta is 0, and if two variables are identical, then the value of this symbol is 1. So this is Kronecker delta symbol. And therefore, what will be the value of delta 1, 1? Since 1 and 1 are the same integer, they match, therefore it falls into this category, and so its value will be 1. On the other hand, if we have delta 0, 1, now since 0 is not equal to 1, it falls into this category, and therefore delta 0, 1 is 0. Now distance between 2 points was obtained to be, and here we have it. We can rewrite it using Kronecker Delta, which is being done to get a future advantage. Here we have 1 and here we have 2 1s, and therefore we can use delta 1 1 here, and delta 1 1 is 1. Here we have a 0 and here we have 1 2, and therefore we can use delta 1 2 here. Similarly for 2 1 we will write delta 2 1 equal to 0 here, and this one can be written as delta 2 2, so that we end up with this expression. If we study this expression, we find that there is summation over 2 dimensions, and it can be written in this way, where I runs over 1 and 2 and j runs over 1 and 2. Now let us check whether what we have written really reproduces this thing. So let us consider this term as we have done it here, written it here. So we start with this expression, and here I is 1 2, j is 1 2, so this can be written in this way. So we have two summations, and this summation let us do first. Now summation over I and dxi has been written here, then this part has been written here, and j goes from 1 to 2, so this term written with j equal to 1 and this term rewritten with j equal to 2. This has been rewritten here. Now we'll sum over I. Let us write these two terms with I equal to 1, and therefore we get here I equal to 1, here I equal to 1, here I equal to 1, and here also I equal to 1. Now we have to rewrite this expression with I equal to 2, and this gives us 2 for I, 2 for I, and here also we have 2 for I and here 2 for I. So we get 4 terms, and if we compare this expression with what we had here, we end up with ds2. So this is indeed ds2. So what we have written here was correct. We now introduce another artifice or a clever notation that was introduced by the famous Einstein. It is called Einstein's summation convention or Einstein's notation. It says that we will not write the summation sign explicitly, and will sum over the index that is repeated. So when we see an expression containing indices that occurs more than once, that is repeats, we have to sum over that index. Let me give an example before rewriting it using Einstein's notation. Consider this summation over I equal to 1 to 3 over ai square. So as per Einstein's summation notation, we can unload or remove this summation sign and instead write it ai square, a simple and compact notation. Since it is square, we write ai twice and identify that the index I is repeated twice. So we have to sum over the repeated index I, and therefore we get these terms for I equal to 1, I equal to 2 and I equal to 3 connected by summation symbols. We take another example. Here summation is over j from 1 to 2 over aij xj. Now here we should not disturb I and keep it as such. As per Einstein's summation convention, summation is dropped and we have aij xj, and then sum over j gives us these two terms. This is for j equal to 1 and this is for j equal to 2. Let us learn one thing here. In this second example, index I is not summed over. It is there and we have to let it be there. It is called free index in the sense that we have no control over it. It is free to assume a value that has been previously decided before we take it for discussion. In other words, its value is pre-decided. It is unique. We can't change it. But look at the index j. What is its value? It is 1, it is 2. That is, it takes multiple values. It runs over values 1 and 2 and therefore it is called run index. It has no unique value. It does not represent any characteristic feature of a system, and hence we can use any other symbol for it. For instance, instead of j we can use r or any other symbol, and still if we sum over this repeated index we get the same value. As this index does not take unique value, it has no value of itself, it is called dummy index. We have to be careful in writing it. Let us illustrate it through an example. Consider x equal to summation over I ai square, and as per Einstein's summation convention we have written it as ai square and then summed over the repeated index I to get a1 square plus a2 square. Again, if a1 is 3 and a2 is 4, we end up with 25 as being the value of x. Consider another quantity y, which is summation over I ai bi, and in Einstein's summation convention we have to unload summation sign and write it in this way. Here I is the repeated index, and if we sum over I over 1 and 2 we end up with a1 b1 plus a2 b2. With these values of b and these values of a we get 25. So this means numerically at least x and y are same, but when we write them explicitly we have to write them in a careful way. Now this is how we can write it. For x we can write ai square, and for y we have to write not ai bi but aj bj, or we can write it as aj square is equal to ai bi. Now what if we write this for x and this for y? Then we have this expression, which means we can cancel ai and therefore we end up with ai bi, that is a1 equal to b1, a2 equal to b2, which is not really the case, and therefore we cannot write it in this way. Now this is because of the fact that I here is 1 and 2, I here is also 1 and 2, but this does not mean that when I equal to 1 here, this I is also 1, it might be 2. So this I and that I do not match. So when we equate them, one has to be kept I if we like to, while the other has to be changed. So let us come back where we left. So this is where we left. In this expression, let us use Einstein's summation convention or Einstein's notation to make it look simpler, and therefore we have to drop this summation symbol, and then we end up with this expression. Now ds2 represents square of the distance between 2 points. dxi is the elemental length along one direction, dxj is the elemental length along another direction, and this is Kronecker Delta, which ensures the fact that in the expression of ds2 there will be no cross terms, but there will only be square terms, and we can write it explicitly in a matrix form in this manner. And also in this expression Einstein's summation convention has been used to give it a compact, simple and elegant look. Notations which are friendly lessen our anxiety, and this has been achieved by Einstein's Summation notation and Kronecker Delta symbol. We had written ds2 for 2D, and how can we extend this result to rope in another dimension? That is, how can we go to 3D? The answer now is obvious. Include x3 in the 2D world of x1, x2. And also the value assumed by I and j, which was 1 and 2 in 2D, will now be extended to 1, 2 and 3 in 3D. Interestingly, the main expression in terms of notation, that is this one, remains unchanged even if we move to 3D, though when explicitly written they differ. Let us go back to geometry now. This is the figure for 2D. We dealt with it and arrived at ds, which is actually under root ds2. The analogous figure for 3D is here. This is x-axis, y-axis, z-axis, and this is dx, this is dy, this is dz, the elemental lengths along the three axes. And the points P and Q are here for 2D, and this is under root ds2 or ds. In 3D, here is P, here is Q, the diagonal of this parallelepiped, and this distance is ds or under root ds2. Now what about the calculation? It is just an extension of 2D calculation, and here it is. So this is the parallelepiped, and this is the distance between P and Q, and parallelogram law of vector addition can be used to end up with this relation, and then we can change the notation to get this one, and an Einstein summation convention can be used to our favor, and then we end up with this relation where we have used Kronecker Delta symbol. Now in this case Kronecker Delta is a 3 by 3 matrix, and it is this one. With mathematics we get a deep insight into physical laws. So to say, with math physics spreads its wings. We have shown a bit of it. Let us now go back to what we were discussing, the concept of distance in Euclidean space. The square of distance is given by this expression. The format describes Euclidean space. Let us collect the points and make a list of the characteristic features that is manifested and displayed by this relation. Euclidean space is described by Euclidean geometry. It is such a space that the explicit expression of distance between 2 points involves no cross terms, involves only square terms, and they are distance square, and these square terms are added, and significantly it does not involve time in the description of space. Again, the quantity in the expression of ds2 which expresses all these characteristics is this one, Kronecker Delta Ij. Now, it is logical to assume that Euclidean space is not the only space we can think of theoretically. Various types of spaces can be formulated, and each type of space will be described by 3 directions which are denoted by dx1, dx2 and dx3. So, in the expression of ds2, dxi, dxj will remain. It will be same whatever be the space, Euclidean or otherwise. Now if that is so, then which quantity represents or indicates changes in different spaces? and that is obviously the quantity that is present here. For Euclidean space it is the Kronecker delta, and for other spaces it is a different thing, and we can call it Gij, and this quantity is called metric, actually metric tensor, and we'll in later lectures talk about scalars, vectors and tensors. So this is the metric, and for Euclidean space this is the Euclidean metric, which is actually the Kronecker delta symbol. So metric is a quantity which describes the fabric of space, the structure of space, the makeup or the composition of space. Its finer details are thrown open by this quantity which is called metric. It tells us how is the space built and what are its characteristics or properties. The essential features are highlighted through this quantity sitting over here. Another important characteristic that Euclidean space exhibits is length invariance, and we already showed it. This is a length, say pq. This length can be viewed from xy or from x prime y prime, which is rotated with respect to xy, or from x double prime y double prime, which is rotated as well as translated with respect to xy. In other words, ds or under root ds square is invariant. So ds is invariant, ds2 is invariant. So Euclidean space is such a space that the three elemental lengths along three directions in case of 3D coordinate in such a way that ds2 or ds is invariant. And this Euclidean space does not require the help of time to maintain or preserve this invariance. So time has no role here. Now a bit of geometry. The point-to-point link generates a line. So a line connects two points and we get one-dimensional Euclidean space. Again, a line and a point not on the line generates a plane, which is a 2D Euclidean space. A plane and a point where the point is not on the plane together generate what we call a 3D Euclidean space. In Euclidean space, Euclidean geometry is valid and we call it a flat space having no curvature, because in this space these two relations hold. Sum of three angles of a triangle is 180 degrees, and this is the famous Pythagorean theorem which says that in a right angle triangle, square of hypotenuse is equal to the sum of the squares of the other two sides. So in this lecture we have spoken of the need of coordinate system. It is needed to describe the space in a systematic, logical and coherent manner. We defined what space stands for. It is the region around us, the stretch or expanse or the neighborhood. Next, we directly went to describe space in 1D, 2D, 3D that were studied by Euclid through his Euclidean geometry and is defined as Euclidean space, which rests upon concepts of point, angle and distance. And we also discussed properties of Euclidean space, namely it is described by a Euclidean metric, which is actually the Kronecker Delta symbol, and also in this space length is invariant. We also stated that to express motion of particle in this space we require coordinates, and the coordinates are represented by real numbers which obey the rules of ordinary algebra, and coordinates are finite ordered numbers. And of course the space is continuous and not made up of bits and pieces. We will end up this lecture in a minute, but one question really should crop up in your mind if you were patient enough to reach this point of time. And that is, do we live in Euclidean space? Is the space around us Euclidean? That is, does the space we find ourselves in follow the Euclidean geometry? We will take up this aspect in the next lecture entitled IN1b. Let me end this lecture with a passage from A Brief History of Time, penned by the gifted and brilliant Stephen Hawking. Galileo, perhaps more than any other single person, was responsible for the birth of modern science. His renowned conflict with the Catholic Church was central to his philosophy, for Galileo was one of the first to argue that man could hope to understand how the world works, and moreover, that we could do this by observing the real world. These are the words of the uniquely skilled Stephen Hawking, who says that we owe a lot to Galileo, who fought for the right of people to observe, to see, to hear, and to interpret the world around us, and not to rely on people who never saw, never heard, never interpreted, but always had so many stories to tell. People who wielded immense power to rule with the sole aim of stifling thoughts and opinions of others solely to keep their show business going on. Thank you.